today is our third part of our video. Previous time we discussed about two parts of theory of intervals, and we have a third part, properties of interval. So let's start our video. So here is the properties of interval. The intervals are precisely the connected subsets of real. It follows that the image of an interval by any continuous function is also an interval. Okay, so here is our second page. This one formulation of the intermediate value theorem. The interval are also the convex subsets of real. The interval enclosure of a subset X subset of real is also the convex whole of X. The intersection of any collection of intervals is always an interval. The union of two intervals is an interval if and only if they have a non-empty intersection, or an open endpoints of one interval is closed endpoints of the other. Example, A comma B's union B comma C is equal to A comma C. Okay, this is a very important thing in theory of intervals. If real is viewed as metric space, its open balls are the open bounded sets C plus R comma C minus R, and its closed balls are the open bounded sets C plus R comma C minus R. Any element X of an interval I defines a partition of I into three disjoint interval I2, I3, I2, I1, I2, I3 respectively. The elements of I that are less than X, the singleton X comma X closed interval is equal to X, and the elements that are greater than X, the parts I1 and I3 are both non-empty and have non-empty interiors. If and only if X is in the interior of I, this is an interval version of the trichotomy interval. So let's move over next slide. So here, complex intervals. What are the complex intervals? Intervals of complex numbers can be defined as a region of the complex plane, either rectangular or circular, maybe both. There are the complex intervals. Okay, understand the complex intervals. This is a very important topic. Integer intervals. What are the integer intervals? The definition said that when A and B are integers numbers, the notation A comma B is in closed interval, or A comma B between these intervals, is used in some programming languages. Pascal, example, Pascal is a programming language in computer. For example, it is used to formally define a subrange type, most frequently used to specify lower and upper bounds of valid indices of any array. Okay, this is the integer interval in mathematics used in computer science. An integer interval that has a finite lower or upper bound, upper endpoints, always includes that endpoint. Therefore, the exclusion of endpoints can be explicitly denoted by writing A to B minus 1 comma A plus 1 up to B, or A plus 1 up to B minus 1. Alternate bracket notations like A comma B or A comma to so on. These notation, these intervals used in computer programming like Pascal, you see, are rarely used for integer intervals. Let's move on our next slide. So, I'll think about degenerate interval. A degenerate interval is any set consisting of a single real number, Aya, An interval of the form a comma a. Some authors includes the empty set in this definition. So this is the definition of degenerate interval. And here is the proper interval. What is the proper interval in mathematics? A real interval that is either empty or degenerate is said to be proper interval and has infinitely many elements. That's why we called it proper interval in mathematics. Here is Diadic interval. What is Diadic intervals in mathematics? Here definition said that a Diadic interval is bounded real interval whose endpoints are j over 2 power n and j plus 1 over 2 power n, where j and n are integers. The Diadic intervals endpoints here and here. These endpoints involving any interval, the interval said Diadic interval in mathematics. Okay. Here are some properties of Diadic interval. Diadic interval has the following properties. First, the length of a Diadic interval always an integer of power 2. Note that each Diadic interval is exactly contain one Diadic interval of 2 is the length. Each Diadic interval is spanned by two Diadic intervals of half the length. Okay. 4. If two open Diadic intervals overlapping, you know that what is overlapping sets. Same here. The one of them is a subset of the other. The Diadic interval can consequently have a structure that reflects that of infinite binary tree. Diadic intervals are relevant to several areas of numerical analysis, including adaptive mesh, refinement, multigrid methods, and wavelet analysis. Another way to represent such a structure is Diadic analysis for p is equal to 2 using for Diadic intervals and these properties. I hope you understand very well Diadic interval. This is very important for higher mathematics, and using MPhil, who a student in MPhil mathematics or MPhil physics or computer must understand Diadic interval. Okay. So here we have generalization multidimensional intervals. So what are the generalizations multidimensional intervals? An n-dimensional interval is defined as a subset of Rn that is the Cartesian product Cartesian product of n intervals. Here I is equal to I1 steric means multiplied by I1 multiplied by I2. Okay. I1 multiplied by I2 multiplied by up to nth In. One on coordinate axis for n is equal to 2. This can be thought of region bounded by a square rectangle whose sides are parallel to the coordinate axis, depending on whether the width of the intervals are the same or not. Likewise, for n is equal to 3, this can be both of as a region bounded by an axis, aligned cube or rectangular cuboid in higher dimensions in the Cartesian product of an n intervals are bounded by an n-dimensional hypercube or hyperrectangle. A facet of such interval I is the result of replacing any non-degenerate interval factor I power k by a degenerate interval consisting of a finite endpoint of I power k. The faces of I comprise I itself in all faces of its facts. The corner of I are the faces that consist of a single point R power n. These are the definitions about our third video lecture. So this is the very important to you, and please understand carefully, attentively, and read descriptions also. And please wait for our fourth video on union and intersection of intervals and some examples to you, that your learning process must be hard in intervals, understanding your process. And stay safe.